All right, continue on with the review, mostly review from general chemistry. Again, what I'm doing here is kind of laying a foundation for why chemical reactions occur, because we're going to start diving really in depth on not just why, but the how, kind of looking at like turn by turn directions of chemical reactions. Now, one of the concepts that you looked at in general chemistry was equilibrium. And what you discovered is that most reactions aren't just A going completely to B, but in reality, it's a kind of mixture of the two, where the rate of the forward reaction is equal to the rate of the reverse reaction. And we get some sort of mixture of A and B. And again, I want to highlight, this is probably specified in general chemistry. That doesn't mean you have exactly half of one or half of the other. There might be certain conditions where that occur, but equilibrium doesn't mean you have 50-50 mixture. It just means that you have a mixture of reactants and products, and the products are being formed at the same rate the reactants, the products are going back to reactants. Now, the way we quantified this was with an equilibrium constant we called K. And that was just simply the concentration of the products raised to the power of the coefficient in their balanced equation divided by the concentration of the reactants. Again, raised to whatever power the coefficient was in the balanced equation. And if we had more reactants or more products, we would take the product of those, multiply the concentrations together. But let's take a look at why does not all of A turn into 100% of B. That's a very rare thing to happen in a chemical reaction. And so in order to look at this, we got to look at the energetics. We got to look at the value of G. So let's set up this graph here. On the y-axis will be G, and on the x-axis will be the concentrations, where we're starting with 100% A here. So only A on the left and only B on the right. Now, assuming this is a spontaneous process, we're going to start with all of A, and we're going to go down, and eventually we hit a minimum value of G. Now, I do want to point out that this process here is spontaneous. At some point, that value starts to go up to form, if we're going to form 100% of B. And going up on this graph is a non-spontaneous process. So at some point, after that minimum value of G is reached, the reaction becomes non-spontaneous. And so obtaining that 100% of B is not favorable. We could get it to happen if we adjusted reaction conditions and overcame that non-spontaneous thing, or non-spontaneous phenomenon. Um, but it just does not become favorable anymore to make 100% of B. Now, where that minimum value of G lies, notice here how it is kind of closer to B. That indicates that this reaction favors B, or what we would say is its product favored. If that minimum value were closer to A, so something like this, so that minimum value here is closer to A, then we would say that it favors A, or be reactant favored. Now, what this means is that there's got to be a relationship then between delta G and equilibrium. And that mathematical relationship is this, negative, or delta G is equal to negative RT times the natural log of the equilibrium constant. And so then we can kind of quantify, so to speak, or look at a trend of the sign of delta G and the value of K. So if delta G is negative, then K is large. And what I mean by that is it's greater than 1, which means that it's a product favored equilibrium. Now, the bigger K is, the more products you will obtain. If delta G is 0, which is very rare, it happens, but it's rare, then K is 1. Sorry, having some technical difficulties. And what that means is the concentration of the reactants equals the concentration of the products, or you have a 50-50 mixture. If delta G is positive, then K is very small, less than 1, which means that you have a reactant-favored equilibrium. Now, what we're going to kind of do is look at comparing thermodynamics and kinetics and how they work hand in hand. Again, thermodynamics is kind of studying the beginning and the end of the reaction. So where we're looking at the energy of the reactants compared to the energy of the products. Kinetics is about how it gets there. How fast will a reaction occur? So if we draw a reaction coordinate, and we have our reactants here, let's call them A, and our products here, B. Thermodynamics is just the measure of that difference of energy. What kinetics tells us is, does the reaction happen very quickly? Like there's a very low energy barrier? Or does it happen slowly? Like it takes a lot of energy to get there. This here is what kinetics tells us. How do we quantify kinetics? So let's say we have this reaction here. A plus B makes C. So it's in equilibrium with C. How fast the reaction occur, or the rate, is equal to some sort of rate constant. I want to make sure that's a lowercase k. So that's not equilibrium constant. Don't mix that up. Times the concentration of A raised to some power. Same thing for B. Concentration of B raised to some power. Now, X and Y, just to reiterate from what you learned in CHEM, are determined experimentally. They are not the coefficients from the balanced equation. Okay? And I'll set your mind at ease right now. You're not going to have to calculate any rate laws. You're not going to have to find rate constants or, compare the rates of 5 reactions and hold one thing constant. You're not going to have to do all of that. You mastered that in GChem. But I'm just putting it up there just to review what kinetics is. Now, again, let's kind of go back and let's use this reaction A plus B making C to illustrate some points here. So let's start with these reactants, A plus B, and they're going to make C here. Now, just based on the energy of those, the energy differences there, would you say that this is an exothermic or endothermic process? So it would be exothermic because the energy of the reactants is less than that of the products. Now, if this is a fast reaction, the activation energy is small. Remember, activation energy is the amount of energy it takes to get from the reactants to the top of that hill. If you don't have that sufficient amount of energy to get up the hill, then you can't get down the hill to get to C. Slow reactions will have a high activation energy. So the higher the activation energy, the slower the reaction. Now, in GChem, you looked at a few ways to lower that activation energy. So what are some factors that affect the rate of a reaction? Number one was temperature. Increasing the temperature increases the rate of the reaction. And generally, um, increasing it about 10 degrees, and this is a very generality or very general observation, approximately doubles the rate. And that's an exponential relationship. What I mean is that if you increase it by 40 degrees, that's not 8 times the rate, it's 2 to the fourth, which is 16 times the rate. Another thing that affects the rate of a reaction is something called the orientation factor. Remember that in order for reactions to occur, molecules have to collide. So they have to collide in the correct orientation in order for that collision to result in a chemical reaction. So let's compare these two reactions here. The goal is to make AB, and we're looking at two different reactants to accomplish that. So in this reaction, in order to make AB, a product, B has to collide with an atom of A. So in the top reaction, it could do that by colliding with this. Okay, that results in a reaction. Or it can collide with this. That results in a reaction. But in the second one, if B collides with this molecule from here, that's not going to result in a reaction. Versus if it collides with A, that does result in a reaction. But you can see that there's more possibility of collisions in the first one, and that results in a faster reaction because there's more collisions that will result in the intended product. And then the last thing that you looked at in general chemistry that affects the rate of a reaction is by adding a catalyst. Simply, a catalyst is something that lowers the activation energy without being consumed. So if we have this reaction here that's got this high activation energy going down to products, what a catalyst will do is kind of cut that hill down and lower the activation energy. Now, one of the cool things that we're going to observe every now and then is if we have a certain set of reactants, let's just say A plus B, is that under certain conditions, those reactants will form either one set of products or one product, But change the reaction conditions and you get a different set of products or a different product. And if you look at this graph here, let's compare. So we're starting with AB, these are our reactants. And I want you to compare the energy of the blue pathway compared to the energy of the red pathway. Look at the products CD and E and F. Which of those products are more stable? You say, how do I know that? Remember the relationship between stability and energy. C and D are the more stable products. Now I want you to look at the hills. Which of those two hills is easier to get over? The red pathway has the lower activation energy, meaning it's easier to get over this hill. So based on what this graph is telling you is that C and D are favored thermodynamically. Remember, thermodynamics is about the beginning and the end because they are lower in energy than the reactants. Not only they're lower than energy than the reactants, they're lower in energy than E and F. So C and D is the more stable product compared to E and F. But if we look at the hills, the kinetics, E and F are favored kinetically because they are formed faster. The activation energy to make E and F is less. It's easier to get over that hill. So I want you to think about this for a second. If I do this reaction, if I take A and B, and I do this under two different temperature conditions. So let's say I take A and B, and I heat it up really hot. Which pathway do you think that's going to go? So remember, what is heat? Heat is a form of energy. So if I heat A and B up really hot, it has enough energy to get over this top hill. Why would it want to go over that top hill? Because it ends up making the more stable products. But let's say I limit the energy. Let's say I keep it at cold temperatures. If I keep it at cold temperatures, what is the only hill that A and B can get over? The only hill it can get over is the lower energy pathway. And so the only products that get made, or the products that are favored, are E and F. So let's kind of summarize that. E and F are favored with low temperatures and short reaction times. That's called kinetic control. We're controlling the outcome of the reaction by controlling the kinetics. C and D are favored with high temperatures. Why high temperatures? Well, because you can get over that hill. And long reaction times. That's called thermodynamic control. Now, I talked about the temperature effect. Why is there a difference in the reaction times? So I want you to think about this, and I want you to look specifically right there. Why would long reaction times favor E and F. I'm sorry, C and D. Well, remember that most reactions, especially in OChem, exist in equilibrium. The longer the reaction progresses, the more chance there is for E and F to go back to A and B. And especially if it's high reaction times, then it's going to go down this pathway. So long reaction times favor the thermodynamic product. Now, I will say, in most cases, the thermodynamic and kinetic product are the same, but we're going to look at, as we progress through OChem, some really cool instances where they are not the same. Okay, so I didn't notice that I didn't say all cases, thermodynamic and kinetic products are the same. There are going to be some really cool exceptions that we're going to look at throughout the progress of OChem, where there is a difference between kinetic control and thermodynamic control. So what we're going to look at for the next few minutes is how to look at a reaction coordinate and interpret what everything means. Because up until now, we've looked at reactions that occur in one step. You go over this hill, and then you get down to your products. But reactions, especially in OChem, often involve multiple steps. What I mean by this is, let's look at this graph on the left here. You could see that there's a initial hill and a valley. That's a step. And then we get to another hill and a valley. That's a second step. And then we get to this third hill and finally the products. So we would say that this occurs in 3 steps. And the hills and the valleys, we designate them with special names. We call any sort of local maxima are transition states. So these are our transition states here. And any valleys, or what we call local minimas, are intermediates. And what we're going to do is look at the difference between them. We do not use those terms interchangeably. I want to highlight that. We don't call transition states intermediates or vice versa, because they have 2 very different definitions. A transition state is a state through which the reaction passes. These cannot be isolated. So in this reaction here, we're substituting a bromine for a chlorine. And so what happens is as the chlorine is approaching that carbon, the bromine is leaving that carbon. And a transition state looks a little bit like the reactant, a little bit like the product. Sometimes it looks like more than one than the other. I'll talk about that in a little bit. But a transition state, this is not something that we can isolate. We cannot isolate this compound with the chlorine sort of bonded to it and the bromine sort of leaving it. And I want to kind of use like a really crude analogy, not crude, more like simple, I guess is a better term. But think of it this way. Think of a transition state like you are jumping up and down. So you jump up into the air and a friend of yours happens to take a picture of you at the peak of your jump. Okay. That peak is what a transition state would be. You pass through that sense of weightlessness, but you are not permanently, you can't like isolate yourself in that. You're not permanently weightless, but the picture that is taken kind of gives you what you look like as you pass through that state. Now, let's compare this to a transition state. I'm sorry, an intermediate. An intermediate intermediates have a certain but very, very, very short lifetime. So in this particular reaction, what is happening here is this bromine is leaving. Okay, it's taking its electrons with it, and we're forming this intermediate. We call it a carbocation. We'll talk more about those in a little bit. And this intermediate is something that we can observe. It doesn't last very long. It has very, very short lifetimes. So short that sometimes we can't actually like pull them out of solution. We can kind of trap them in certain ways. I don't want to get too advanced in this, but there are ways that we can analyze to know that they actually exist, albeit very, very briefly. Now, one thing I want to highlight here as we look at this energy coordinate, I want you to look at the hills. What would you say about the rate of this first step compared to the rate of the second step? Hopefully you're saying, well, that first step has a big higher activation energy, and this second step has a lower activation energy. The first step takes a lot more time. It requires a lot more energy. And the second step, much lower activation energy, much quicker. Why do you think this is? I'm kind of taking a rabbit trail here. Why do you think it takes more energy to go from this chemical species to this one? What do you notice about that carbocation and that carbon in the middle with the plus charge? It doesn't have a full octet. So we're going from a carbon that has a full octet to one that doesn't. That requires a lot of energy in order to break that bond and have carbon exist without a full octet. So that's why that step has a higher energy. And if you look at the difference now going from this intermediate to the product, why does that not require a lot of energy? Well, I'm going from something that doesn't have a full octet back to something, a carbon that does. So that doesn't require a whole lot of energy at all. Now, to kind of end this discussion with analyzing reaction coordinates, I want to look at something called the Hammond postulate. And the Hammond postulate basically says the transition state of a reaction or of a step more closely resembles the chemical species, and we'll say reactant or product, it is closer to in energy. Now, what do I mean by this? Let's again look at this reaction. We talked about it earlier. So look at where that transition state is. That transition state is a lot closer in energy to the reactant than it is to the product. So it looks a little bit more like the reactant here. Now, as I get closer and closer to the product, notice how that looks a little bit more like the product. So in an exothermic process, the transition state looks a lot more like the reactant than the product. In an endothermic process, the transition state is closer in energy to the product, so it looks a lot more like the product than it does the reactant. Now to set up where we're going to be going, in our next set of lectures is I'm just going to quickly introduce like some of the most common types of reactions that we're going to see in OChem. And the reason I'm highlighting this now is because we're pretty much going to be spending the rest of this semester and next semester talking about chemical reactions. We're going to deviate every now and then, but you know, I'd probably say about a good 80% of the rest of our time, we're going to be talking about reactions and how reactions progress. So I'm just going to briefly introduce the types of organic reactions. So we're going to look at addition reactions. So as this name implies, we're going to be adding stuff to a reactant. So here we're going to take a compound known as ethene or ethylene, react it with HBr, and a hydrogen will go to one side, bromine will go to the other. We add that HBr across that double bond. We'll look at the reverse process, elimination. This is where we take stuff away. So let's take this alcohol, for example, and I'm going to specifically draw that hydrogen there. I know that there's two more, but I want to specifically draw that because in this reaction, we're going to heat it up with a bunch of acid, and we're going to eliminate two groups. We're going to eliminate that H and that OH to get this double bond, to get ethene. So essentially, I've eliminated water, H and OH, from that reactant. And we're going to look at substitution reactions. Substitution reactions, think of it like, like watching a basketball game. What is a substitution in that respect? Well, one player goes off the court, one player comes on the court. It's the same thing with chemical reactions. We'll have something that we're going to remove from the court, so to speak, and something we're going to replace it with. So here, we're going to replace this chlorine. And so now the OH of water is going to be bonded where the chlorine used to be. And then the chlorine is going to be bonded where the OH of water used to be. So it's kind of like switching partners there. And then we'll spend a little bit of time looking at rearrangements. So we start with a compound like this. We heat it up, and the atoms in this carbon chain rearrange. What you want to start doing now is get good at looking at reactants and products and determine what kind of reaction occurred. Because if you know what kind of reaction occurred, then in your mind, you can start forming, well, how did that happen? What bonds had to have broken and what bonds would have had to form, and how would they do that? We call that a reaction mechanism. And that's what we're going to be going into in our next set of lectures.